It's my pleasure to introduce Yash Deshmukh from Columbia University, and he's going to tell us about a homotopical description of Deligne-Mumford compactifications. So take it away, Yash.
Yeah, thanks for the invitation. Thanks for the opportunity to speak. So as the title suggests, I'm going to present a new description of Deligne-Mumford compactification. So this description is going to be somehow in terms of expressing it as a colimit of spaces made out of uncompactified moduli spaces. So, I mean, one geometric consequence of what we are going to prove is going to be that the Deligne-Mumford compactification is homotopy equivalent to a geometric realization of a simplicial space. And this simplicial space is going to have n simplices, which are given by n nested graphs. So hopefully I'll have time to talk about what this n-nested means as we go along. And these graphs are going to have labels from the uncompactified moduli spaces. Okay, so here I've been saying Deligne-Mumford and uncompactified spaces, so on. So let me just point out this. I'm calling Deligne-Mumford compactification. And you should think of it as just usual moduli space of stable nodal curves with mark points, and some of the mark points are designated as inputs and some of the mark points are designated as outputs. And this M frame GKL, these are somehow framed surfaces. So I'm going to think of them as surfaces which have input boundaries and output boundaries. And all the boundaries are supposed to carry some parameterization, but these things will become clear. At some point, I will say precisely what the moduli spaces are. Okay, so this is somehow just to orient where we are going. So just for preview. But really, the description we want to give is going to remember much more than just the homotopy type of the Deligne-Mumford space. So it's actually going to remember some algebraic data. And the idea is try to express the Deligne-Mumford compactification as a consequence of doing some algebraic operation. So that's going to be somehow the theme. So let me just start by mentioning some features of this description that individually these features have appeared in several works, but the union of all these has not appeared in a single description. And our description does cover all these 3 points. So the first part, so these features are we work with. So the first point is we always work with moduli spaces or stacks. I mean, depending on the case, not just chains on moduli spaces or homology of moduli spaces, etc. So we actually work at the level of topological spaces or stacks. The second point is we always work with moduli spaces or operations that have both inputs and outputs. So this is especially important coming from Floer theory, because whenever we define operations in Floer theory, we want to write down Floer's equation on a surface, and that requires us to choose some negative ends and some positive ends. So we always work in an algebraic framework where you can incorporate this feature that there's always inputs and outputs of your operation. Okay. And the third point I want to mention is we work with all genera, not just genus 0. So there have been descriptions which have individually incorporated one of these points, and I will briefly mention them later on, but all three of them appear in our description. So that's somehow something new about the description. Okay, so this is roughly what I'm going to talk about. So are there any questions about this? Great. If not, I will start with motivating why we care about these problems. About giving a description of this compactification as some algebraic operation. And the motivation comes from looking at mirror symmetry. So Kontsevich has this well-known homological mirror symmetry conjecture, which states that if you have mirror pairs of Calabi-Yau manifolds, then Fukaya category of the first one is equivalent to the derived category of covariant sheaves on the second one. So, I mean, if you want to be completely precise, you should probably say like some sort of idempotent completion of twisted complexes, but let's not worry about it. So the point is, it gives an equivalence between Fukaya category of X and the derived category of covariant sheaves of X check. But if you look at how mirror symmetry appeared in mathematics, one of the first instances was actually equivalence between some numerical invariants. So, for instance, the first computation used the prediction that Gromov-Witten invariants of genus 0, namely counts of rational curves in your symplectic manifold, they should match with the period integrals of the mirror. And more generally, you can expect Gromov-Witten invariants on one side. So these are some enumerative counts. They match with something that I'm just going to call BCOA invariants of the mirror. So these are some invariants related to variation of complex structures on the mirror. So there's this enumerative mirror symmetry, which is predicting equivalence between some numerical invariants. And the question is, does this categorical version of mirror symmetry somehow imply the enumerative mirror symmetry? Because we care about some numbers being equivalent because that helps us compute. And in Kontsevich's original mirror symmetry program, somehow this was implicit that this should be possible to do. And Kontsevich, in fact, has a proposal for how to do this. And the proposal is that we construct something called categorical enumerative invariants. So these things are going to be some invariants associated to a category. So you start with a category which has certain nice properties. So this category is going to be either smooth Calabi-Yau or compact Calabi-Yau. It's a infinity category. So for our purposes, we don't precisely need to know what the meanings of these terms are. Just understand that these are some properties that are usually satisfied by categories which appear in homological mirror symmetry. And idea is that you start with some category which has this property, some abstract category, and you assign to it something called categorical enumerative invariants of C. And this construction should be so that when you take C to be the Fukaya category of X, you should get back Gromov-Witten invariants. And when you take C to be coherent sheaves on X check, you should get the BCOE invariants, which are the mirror to Gromov-Witten invariants. So if we can carry out this construction of categorical invariants, then we can use homological mirror symmetry to deduce enumerative mirror symmetry. Okay. So now how he also kind of outline what should be steps of this construction. So the first step is going to be we start with C and construct a topological field theory. So from C construct. So topological field theory, which this is also commonly called TCFT, and this you should think of as some field theory where your operations come from chains on moduli spaces of framed Riemann surfaces, on compactified Riemann surfaces. So this is what I mean by TFT, and I'm just going to write here action of the uncompactified moduli spaces. So what this means will again become precise later on, but let me just mention here that this TFT, constructing this TFT amounts to constructing an action of M-framed moduli spaces. And the second step is going to be under suitable hypothesis, under suitable hypothesis, extend this action, extend to an action of the compactified moduli spaces. So okay. And in this talk, I'm going to talk about some aspects of the second step. Okay, so is there any questions so far? Yeah, if not,
Sorry,
yeah.
I just have one question. So since you mentioned that you want to construct the action of moduli space of all genera, does this construction give more than just Gini zero chromosome invariants?
So yeah, when I say I construct actions, so these are going to be actions purely at algebraic level. So they are going to be on some sort of Hochschild chains or something like that. So that they're not, as per se, they are not actions that will encode Gromov-Witten invariants. But if you are able to match the Hochschild chains with symplectic cohomology or singular cohomology of your manifold, then these actions will actually help you recover higher genus Gromov-Witten invariants also, not just genus zero.
Okay.
Okay.
Actually, can I just ask, so in the second step, just kind of on the algebraic level, is it, if the hypotheses are satisfied, is it supposed to be sort of unique, or is there supposed to be sort of several different possible choices?
No, I mean, there is a choice involved. So I will mention something about it, but yeah, you need to choose some extra data. I mean, you need to have some extra data in order to make this extension, and the choice of data is not canonically determined always. Yeah. Any more questions? Okay, so let me start making these things slightly more precise. So I'm going to start with saying what these moduli spaces are. So the first kind of moduli space we want to consider is the framed Riemann surfaces, M-framed GKL. So roughly you should think of them as these moduli spaces you see on the right. And these are going to be just moduli spaces of Riemann surfaces. So Riemann surfaces of genus G. They have K input boundaries, L output boundaries. So in total, they have K plus L boundary components, K of which you designate as inputs and L of which you designate as output. And crucially, you take an analytic S1 parameterization. So analytic S1 parameterization of the boundaries. So each boundary carries an analytic S1 parameterization. And the why we want this analytical this parameterization is, if you take now two Riemann surfaces, then this S1 parameterization allows you to glue them along the boundaries and gives a unique complex structure on the glued surface. So that's why we are carrying the data of analytic parameterization. So yeah, in this figure on the right, I mean, I've tried to highlight the parameterizations using like these blue boundaries with and the markers kind of indicate the base point of the parameterization. So, I mean, the price we pay for carrying this analytical parameterization is that the moduli space now becomes infinite dimensional, because the space of parameterization is not finite dimensional. But what I claim is it in fact has a finite dimensional homotopy type. And homotopy type is the only thing we are going to care about. So it's still okay to carry this parameterization. So the claim is that it has a finite dimensional parameterization. And the way you see this is, let's consider the moduli space of just Riemann surfaces with mark points. So genus G Riemann surface with K input and L output mark points. So they have no boundaries. And I'm going to construct a map like this and analyze its fiber. So the way you construct this map is you start with your surface with boundary parameterizations, and you just take the same surface and you just take the same surface and you glue in these disks at each boundary point, and you glue these disks using the parameterization of boundary. So at each boundary point, you are going to glue a unit disk using the parameterization of the boundary and give take a mark point at the center of the disk. So this is going to give you the corresponding disk in the Riemann surfaces without mark points. This is the map from framed Riemann surfaces into Riemann surfaces with just mark points, no boundaries. And the claim is that the fiber of this map is going to be homotopy equivalent to a torus. And the way you see it is, let's pick some surface below here, which is just a surface with mark points. And the fiber is basically all ways of choosing charts around your mark points, essentially. And this choice of chart is basically just a choice of marker at each mark point, because once you fix the positive real direction of your chart, the chart is determined up to a the spaces of charts is then contractible. So so the claim is that here fiber is homotopy equivalent to a torus. So the moduli space of Riemann surfaces with mark points is finite dimensional, and the fiber has some finite dimensional homotopy types. So this gives us that this big moduli space of frame surfaces we are considering actually has a finite dimensional homotopy type. Okay. So this is the moduli space of frame surfaces. Let's come to the second kind of moduli space we want to consider. So these are going to be M-bar frame GKL. So these are similar to the frame moduli space, except that we now allow stable nodal curves. Okay, so these are genus G, K input boundary components, L output boundary components, each boundary component carrying an S1 parameterization, but you also allow stable nodes, stable nodal curves, and these nodes are assumed to be away from the boundary. So when I say stable, this means that there are finitely many automorphisms which preserve all data. So in particular, whenever I say automorphisms, it's supposed to preserve the boundary parameterization. So, and these as I said, automorphisms are also assumed to preserve the boundary parameterization. In particular, as soon as you have a component which has a non-empty boundary, your automorphism has to fix the boundary parameterization, and by analytic continuation, the automorphism has to fix the entire irreducible components. So any component which has a boundary component is just fixed by any automorphism. So the only non-trivial part of automorphism group comes from irreducible components that don't have any boundaries. So in particular, you see the things like this disk with one nodal point and one output boundary. They might seem like they are unstable, but in fact, in this setup that we are considering, these count as stable curves because we also remember the boundary parameterization. Okay. So again, using this S1 parameterization, we are able to glue the stable nodal curves. And as I've shown here, sometimes when you perform this gluing for nodal curves, you might end up with some spheres which are unstable. And since we only consider stable curves, you're supposed to stabilize. If you create some such component as a result of gluing, you stabilize, as I've shown in this picture. Okay. Okay. And so the most important thing about this moduli space is this moduli space, in fact, has the homotopy type of just usual Deligne-Mumford spaces. So this has and again, the way this map is constructed is you start with a stable nodal curve and then just glue unit disks on the boundary components, giving mark points at the centers of the disk. But the claim here is the fiber is not just a torus anymore. The fiber is in fact contractible. So the fiber is homotopy equivalent to a point. And just to illustrate what is happening here, I won't go into detail, but let me just point out what the point is, what is happening. So let's consider some stable curve with a mark point. And now when you look at the fiber is going to contain curves like this. Right. And you might think that this choice of parameterization on boundary is giving me an S1 choice. But the fact is the fiber also contains things like this. Okay. So here you see that this S1 choice of parameterization you had, this S1 family is somehow already null homotopic inside the big moduli, because you can just kind of create a node here and trivialize the S1 family. So that's why the choice of chart is not an S1 anymore in this case, since we are allowing formation of nodes, it just becomes homotopic to a point. The fiber is null homotopic, and hence we get a homotopy equivalence to the usual Deligne-Mumford spaces with mark points. Okay, so is there any question about this? Great. So yeah, so this is the model we are going to use for Deligne-Mumford spaces, because it turns out that it's easier to relate it to the frame modular space of surfaces. Okay, so as you might have noticed, I've started talking about gluings of these Riemann surfaces, and this is the algebraic structure we are trying to capture. We are going to try to capture, and the algebraic gadget we use to do this is called prop rods. So prop rods are somewhat classical, somewhat well-studied objects in algebraic topology. And if you are familiar with op rods, prop rods are just generalizations of op rods, which allow for operations which have multiple inputs and multiple outputs. So op rods correspond to operations which only have multiple inputs and a single output, but prop rods allows multiple inputs and multiple outputs. So a prop rod P is going to be a collection of spaces, so P, K, L. For every pair of natural numbers K and L, you are going to have a space PKL, and we think of this space as the space of operations with K inputs and L outputs. Okay, this is a collection of spaces. And graphically, we think of it as I've indicated here on right, where we think of it as a graph with a single vertex with K input legs and L output legs. Okay, now once you have two such operations, so let's say you have PKL and PMN. There are a number of ways of identifying some inputs of the first one, some outputs of the first one to some inputs of the second one. So graphically you can write it like this, where some of the inputs of the first one, let's say S of the inputs of the first one, are identified in some order with some inputs of the second one. And the data of prop rods also includes the information of how to compose your operations for every such way of plugging outputs into inputs of the next operation. So the data of proprod also includes composition. So this composition is going to be indexed by G, which is just a way of gluing some inputs, some outputs into inputs. So for every way of doing that, you have a composition from PKL cross. Okay. So for every way of plugging some outputs into inputs, you get a composition. So this is the data of data of a proprod. It's collection, these spaces of operations and ways of composing them. And of course, these compositions are supposed to be associative. And there are more conditions involving equivariance and some symmetric group actions, but I'm just going to ignore them for now because they are not so crucial to our discussion. So this is what a proprod is, and we have already seen several examples of proprods. So let's point out let me point out the proprods of framed Riemann surfaces. So the spaces of operations with k inputs and L outputs is just given by just considering all surfaces with k inputs and outputs. You just take disjoint unit over genus and just put together all surfaces with k inputs and L outputs. And the proprod composition is given by gluing, as you would expect. And this forms a proprod. So this is the proprod of frame Riemann surfaces, which we denote by M frame. Similarly, you can form a proprod out of the stable nodal Riemann surfaces by just considering all nodal curves with k input boundaries and L output boundaries, and again composition given by gluing. Now there's going to be one more type of proprod that's going to be important, and this is positive boundary M frame. So what this means is we only consider Riemann surfaces which have at least one output. So the spaces of operations with k inputs, L outputs, these are declared to be empty when L is 0, and they are as above in M framed for L positive. And the point is, if you take two Riemann surfaces, both of which satisfy the property that they have at least one output, their gluing also continues to satisfy the property that it has at least one output. So these surfaces of this collection of surfaces which have at least one output, they are closed under gluing, and in particular, they form a subproprod. And that is the subproprod we denote by positive boundary and framed. And similarly, you can talk about negative boundary and framed, which is Riemann surfaces which have at least one input. So this is going to be empty if k is 0 and as above otherwise. So, okay, the second one is probably not going to play much role, but the first one is something that will feature later on. So these are the examples of proprods that we have seen. I think they're pretty natural examples. So like any algebraic structure, why we are interested in proprods is because they're representations of their actions. And so let me say what action of a proprod means. So if you have a proprod P, its action on a space is just maps as follows. So these are PKL. So you take kth power of x, you map it to lth power of x. So you take an operation in P and you take k inputs from x, then the action is supposed to give you L outputs in x. This is what action of a proprod means. And of course, these maps are supposed to be compatible with compositions in P. So an alternate way of saying this is as follows. So for any space X, we can, for the space X, we can form an endomorphism proprod. which assigns. So the endomorphism properad has, as its KL operations with K inputs and L outputs are literally just all continuous maps from K copies of X to L copies of X. These are just continuous map from X to the power K to X to the power L, and you compose them in the obvious manner. So this is the endomorphism properad associated to X, and an action of P on X. So an action of P on X is basically equivalent to a properad map from P to end X. This is the alternate way of saying what action of a properad is. Namely, you just get a properad morphism into the endomorphism properad of your object. Okay, so this is action of a properad on a space. So strictly speaking, all this discussion was for properads which are in topological spaces. So topological properads. So you can also talk about properads in other categories which have a good notion of tensor product, like chain complexes and graded vector spaces and so on. So let me not elaborate on this, but you can talk about properads in other categories. Okay, so any questions so far on this?
So are these properads the sense in which you mentioned at the beginning, one of the features is that you work with moduli spaces and stacks instead of the chains or homology. Is this the sense in which you were saying that?
So I'm going to talk about properads in topological spaces. So this is the sense in which we work at level of spaces, not chains. So yeah.
Thanks.
Any other question? Okay, so if not, let me go back to these steps that I described in just 2 lines earlier and try to say now in this language of properads what the steps look like. So the first step was, remember, concerning constructing a topological field theory from a category. And the way we say it in language of, the precise results are as follows. So let's say C is either smooth Calabi-Yau or proper Calabi-Yau. A infinity category. Then the Hochschild chains on C is has an action of so in the smooth case we get an action of surfaces with at least one output, and in the proper case we get an action of surfaces with at least one input. So to spell it out, spell this out, what this means is we are going to have maps as follows. So so these actions are chain level, has an chain level action. Okay, so to spell this out, it's going to be maps like this. So from modular space of frame surfaces, and you get such maps. In the smooth case, you get them when L is at least 1. And in the proper case, you get them when K is at least 1. So smooth case, at least 1 output, proper case, at least 1 input. And so let me give citations. So the smooth case is an upcoming work. So work of Kontsevich, Takeda, and Lassopoulos. And the proper case is a well-known result of Costello. So this is the first step carried out in these works, where they show that you start with either a smooth Calabi-Yau or proper Calabi-Yau category, and then you get action of the prop rod of framed Riemann surfaces. And the second step is going to be to show that under suitable hypothesis, these actions, which essentially amount to some sort of positive boundary TFT, these actions extend to actions of the compactified surfaces. So these are going to be maps as follows, these compactified surfaces. And once we have such an action, then we have this action gives us candidates for defining categorical enumerative invariants. So this action gives a way of defining categorical enumerative invariants associated to chains inside the Deligne-Mumford compactification. Because remember, we mentioned that this modular space is just the same homotopy type as the usual Deligne-Mumford compactification. So if you give me a chain inside the Deligne-Mumford compactification and certain classes in the Hochschild chain, then I can tell you what the associated categorical enumerative invariant has to be using this map. Okay. And so the point is, such extensions are not always possible. We actually need some extra data for such extension. And this extra data is something which again Kontsevich has suggested what the extra data has to be. So to understand what the data is, let's go back to the M-framed action of M-framed action of the framed M-framed action on the Hochschild chains. So in particular, the M-framed action involves action of M-framed 0, 1, 1. So these are genus 0 curves with 1 inputs and 1 outputs. So basically, annulus with input boundary and an output boundary. And the TFT structure gives us action of such annuli. These are annuli like this. Now notice that because of this boundary parameterization, the moduli space of such annuli is homotopy equivalent to a circle. And so what the M-framed action is in fact giving us is some sort of up to homotopy action of chains on a circle on your Hochschild chain complex. And what this extra data is going to be is homotopy, trivialization of homotopy trivialization of this circle action. And the way we understand it, I mean, the way I interpret it in this case is you can extend the action to the compactified moduli space of annuli. So now earlier these were just non-singular annuli. So the homotopical trivialization is going to be an extension of this action to possibly nodal annuli. So this involves usual annuli, but also involves this nodal annulus with 1 input and 1 output. So as I said before, the moduli space of annuli, non-singular annuli was homotopy equivalent to an S1. So when you add this nodal annulus, the moduli space in fact becomes homotopy equivalent to a disk. So which is same as homotopy equivalent to a point. And we have the homotopy extension is going to be this homotopy trivialization of the S1 action induced by M-framed. Okay, so is there any question about this part, about this extra data that we are going to need to extend the action from M-framed to M-bar framed? Okay, so yeah, and again, this goes back to the question that Kyler asked, namely the choice of this extra data is not unique. Usually you can get hold of at least one trivialization using some geometric input, but typically it's not clear what the correct choice of trivialization has. I mean, it's not clear if there's any particular choice of trivialization that's distinguished. You just have many trivializations typically.
Actually, sorry, can I ask one more question? So if you're interested in these categorical enumerative invariants, like at what point can you pass the homology? So if you pass the homology, like could you just say that the sort of you have sort of some homological prop and that already contains the enumerative data, or is it sort of there more information in this chain level map that you?
Yeah, no, I think the homological prop already contains more data. I mean, you have homology classes in the compactified moduli spaces, which are different from just the classes of the uncompactified space. And so, yeah, maybe, I mean, maybe what's worth pointing out here is this extension geometrically, you should just think of it as somehow extension coming from counting. So if you want to consider the action of a particular chain sigma inside Deligne-Mumford, let's say you take some sigma inside the compactified frame moduli spaces. The way geometrically we think of this action is just consider just count stable nodal curves where the mark point. Okay, let me actually let me not take sigma here. Let me take sigma inside the usual Deligne-Mumford space. So if you have sigma in the usual Deligne-Mumford space with mark points, not boundaries. So in this case, geometrically, we just think of this action as counting stable curves where the domains lie in sigma. And that's why, I mean, since this action is defined in terms of such counts, I'm claiming that it somehow captures some enumerative information. That's the point. So yeah, in particular, I mean, even passing to homology, you already have some enumerative data being encoded there. Yeah.
I see. I guess I was just wondering because sometimes there's sort of extra sort of Massey product type information in the chain level structure that you don't, that you lose when you pass the homology. So I was just trying to understand exactly where if there's some sort of loss of information in passing homology.
Yeah, I mean, there is going to be loss of information from going from chains to homology, but already, like, you can also talk about enumerative counts coming from homology classes in moduli spaces instead of chains in moduli spaces. So in that sense, homology also has some enumerative data, but of course, yeah, I mean, as you point out, you are going to lose some information when you pass to homology.
Yeah, I see.
Can you hear?
Yeah.
Yeah. So you don't expect that this extra data will exist when you're considering the action on like symplectic cohomology of a Liouville manifold or something like that?
No. So yeah, typically this extra data is available when you are on a compact manifold. Because I mean, in geometric setup, the action of this non-singular annulus just corresponds to the BV operator. And this homotopical trivialization is somehow a trivialization of BV operator, which is not always there for symplectic cohomology, but it's there when you consider symplectic cohomology of a
Yeah, I mean, I think formally I understand, but I never understood like how compact versus non-compact, or like what is this extra data that comes in when you have a compact manifold?
So, okay, so maybe it's useful to slightly go back and let's see what is happening here when we are in the smooth Calabi-Yau case. So you'll see that there's a restriction that you always need to have at least one output. And geometrically, what this corresponds is that of smooth Calabi-Yau you somehow think of, let's say, of open open exact symplectic manifold with cylindrical and Hochschild chains correspond to symplectic cohomology. And now to define operations using some curves, you are going to need to choose a flourish or semi-negativity. Yeah, but it satisfies some inequality to make sure that maximal principle holds, which is again necessary to make sure your moduli spaces are compact. And so this forces, by Stokes' theorem, the fact that you need to choose such a form forces you to have at least one output. Whereas if you are in a compact case, there's no restriction on what beta you can choose. You don't need to apply the maximal principle necessarily, so you can choose your beta to be whatever. In particular, you can define it for surfaces which don't have outputs. And that is why you can do such an extension in the compact case where we can talk later.
Yeah, maybe you keep going and then there'll be time for questions after the talk.
So yeah, great. So the point is, if you have homotopical trivialization, then you can extend your M-framed action to an M-bar framed action. And this is, we are going to prove some version of this theorem, some version of this statement. Okay, so let's come to the main statements of the theorem. And there's a technical caveat where the theorems are going to be not stated in terms of not properties, but something called input-output property, which I abbreviate as IO property. And the main difference here is there are no operations, like there is no data of operations with 0 inputs and 0 outputs. That's the difference with property. So in particular, your IO property might actually contain some operations which compose to an operation, which might compose to an operation with 0 inputs and 0 outputs. But since we don't have the data of 0, 0 operations, such compositions are also not included as part of the IO property. So okay, this is some technical condition that's needed for the proof. I wouldn't concentrate too much upon it. So let me state the theorem. So the first part of the theorem. This is going to describe the extension from M-framed to M-bar framed. And the way you do it is, let's consider a subproperad of this called M-framed unstable. So these are going to be, this is the subproperad of Riemann surfaces which have shapes that I'm now going to draw. So you have annuli with one input, one output. You have annuli with two outputs, annuli with two inputs, so all annuli. And you also have these trace and co-trace operators. So this is kind of BV. The annuli with two outputs is like a co-pairing, the annuli with two inputs is pairing, and these two operators are trace and co-trace operators. So let me just note that these three moduli have homotopy types of S1, and these two have homotopy types of just points. Similarly, you can consider the moduli space of unstable moduli space of nodal surfaces in the unstable range. So these are again going to include similar things. And here, all of them have homotopy types of point. And what the theorem says is that you consider M-framed, you consider this subproperad of unstable, subproperad of surfaces in the unstable range, and then you push out along inclusion of this subproperades. So when you push out, the result is going to be the M-bar framed properad. So this is a homotopy push out. Is a homotopy push out in IO properties. Okay. So this is telling you how to express M-bar framed as a certain push out, where you take M framed, you go to the subproperad in the unstable range, and then you push out to include all the nodal curves also in the unstable range. So notice that the effect of this push out is basically trivializing these families. So we had S1, S1, S1 here, which became point, point, point here. So essentially we are kind of providing trivializations of these S1 families, and the claim is that result is going to be M-bar framed. So let me just point out that we are actually not, I mean, it's not just the data of trivialization of this annulus as it was in the proposal by Kontsevich. We are also including the data of these trivializations. And the fact that these trivializations are contained inside a properad is essentially saying that the trivializations are compatible with each other in the sense that they satisfy some snake relation. Okay. So this okay, so you had these three S1 families. You provide trivialization of each S1 family. Further, the trivializations are going to be compatible with each other. Then you can extend your M-frame property to M-bar frame property. So let me just mention what this means at the level of algebras, because that's what we care about. So let me just quickly copy the push out. And let's start with something which is an algebra over M-framed. And what it's saying is the M-framed action restricts to action of M-framed unstable on your V. So it includes action of these things. And having a map from here basically means that these actions on V are trivializable. In that case, the push out property is going to tell you that when these actions are trivializable, you have an induced map from the right corner of the push out, namely the M-framed. So this is equivalent to having a M-bar framed algebra, M-bar framed action on V. Okay, so at the level of algebra, you use this push out square in this manner, except that this is only a heuristic because this only holds up to homotopy. Because this push out is not a genuine push out, it's only a homotopy push out. Okay. And in some sense, we should really only care about homotopy push outs, because whenever we are going to construct these actions in Floer theory, these actions are typically, they involve choice of some auxiliary data. And this choice of auxiliary data means that your actions and all the structures you consider are only well defined up to homotopy. So it is indeed desirable to have a statement which is homotopy coherent, which is what our statement is. But that means that you can't on nose apply the universal property of push out. It only holds up to some homotopy coherences. Okay, so this is the statement of the first part. Any question? Okay, so let me state the second part. So remember the actions constructed in the first step were not actually actions of entire M-frame. They were actions of this positive boundary or negative boundary versions of M-frame. And the second part is going to tell you how to go from this positive boundary M-frame to the entire M-frame. And there's an analogous statement for negative boundary, but I'm just going to state this one. And the way you do it is you again consider the subproperad of surfaces in the unstable range, and then you push out to some new subproperad. So let me write the surfaces which are included here. So here you have all the annuli. Remember, this is surfaces with at least one output. So in particular, you don't have the annulus with two inputs and the disk with a single input. Both of them are not included. Rest of the things are here. This is positive boundary M-framed unstable. And what the second property consists of is okay. So the only difference between M-framed NOP, which is read as no pairing, and M-frame unstable is that the M-frame NOP has no pairing. So it excludes the annulus with two inputs. But I mean, you will notice that M-framed NOP is already a subproperty, and this is the subproperty that we push out along. So you start with positive boundary M-framed, you have the subproperty of annuli and disk, and then you push out along this inclusion inside M-framed NOP. So basically, you are only adding this trace operation, and once you add the trace operation, the property, the homotopy push out coincides with M-framed. And so let me just point out here that adding the trace operation, I mean, the fact that this trace operation is sitting inside the subproperty essentially is saying that this relation is satisfied. Okay. So if you have an algebra or positive boundary M-framed, to restrict, to extend it to an action of M-framed on your space, the only thing you need to do is you need to figure out what is a trace operation which is compatible with the co-trace operation in this manner. And then you have an extension of actions. So that's these are the statements of the theorem. So I have a few more things about some technical remarks and the proof, but I think I only have 2 minutes left. So unless somebody asks a question, I think this is a good point to stop.
Okay, so let's thank Yash for the talk. Questions?
I can ask one.
Okay.
So there is this, there is the compactification that we used in paper with Mohammed and Yuval, this KSV compactification. What is so that also forms an operad, and I think if you restrict to the one output spaces in your properad, you also get an operad.
Yeah.
What's the relationship between?
No, these spaces are just homotopy equivalent to those KTV spaces. So just, I mean.
But then you said something that I couldn't understand. You said that it was actually homotopy equivalent to the Deligne-Mumford space, not the, you said that you lost the TNs.
Yeah, so that's the M bar framed. So here I'm saying that M framed have the same homotopy type as the.
No, of course, and yes, that's I know, but that's okay. I should rephrase my question as what's the relationship of that operad with the compactified operad? Then is there a relationship, or is, well, I guess you're explaining the relationship. Maybe.
Yeah. I mean, naively you have a map by just like forgetting all the markers in the KTV moduli space into Deligne-Mumford space. And yeah, I'm explaining that that map is in fact some kind of homotopy push out by just trivializing the S1s.
Okay, thank you.
Yeah, okay.
Any other questions for Yash?
I can ask one more.
Please, go ahead.
So how would you construct an action of this on something like symplectic cohomology? Like I'm.
That's a very good question, and I don't have a good answer for it. Yeah, I mean, I'm not sure what the correct structure to look at look at is whether proprad is a good structure, because I mean there's this problem of composition in proprads along several inputs and several outputs. And if you naively try to think about making, so I mean, ideally we would have a manifold with boundary model of M-framed acting on symplectic homology. So in this case, something like a KTV model acting on symplectic homology. But that would mean that we want to make sure that these compositions across several inputs, they appear as some sort of codimension 1 strata in your modular spaces, which seems hard to incorporate right now. So is it clear what I'm trying to say?
I don't know. It's not really. But I think I might be missing something very basic.
No, I mean, so let's say some input, some breaking like this. This is a single proprad breaking. So this is like single operation of proprad. You can't do it like you first glue the first one and then glue rest of the boundaries, because that would be somehow gluing across a cycle. So like proprad doesn't allow you to glue inputs and outputs of the same thing with each other.
Yeah, but I think I'm confused about something like much more basic. I mean, the way the operad structure is defined in the KSV compactification is it kind of is very natural with respect to gluing and all these things in Floer theory.
Yes.
But this I don't understand. Like it's a very similar looking structure, but it's at the same time very different. Like what the Hamiltonians will.
Yeah, I mean, like constructing operations is probably not that hard. So you just choose like Hamiltonians that satisfy suitable condition like this H3 plus H4, like greater than or equal to H1 plus H2. And then you choose some auxiliary data, Floer data, like this Hamiltonian valued one form on your surface, and you just define.
No, but these broken things don't appear in the boundary of your, like when you can't converge to the boundary of the moduli space, can you? I mean, there's not a gluing parameter. You just like glue in this structure. You don't have like a, so the composition that I'm used to, you just kind of like you don't do anything. You just put them on top of each other without actually gluing anything.
Right,
kind
but
of like
even if you do that, that's kind of in the naive KTV, I mean, in the KTV compactification, that thing is a codimension 2 boundary. When you just
so I have no idea how to do anything in this compactification. In this I should say operad structure.
Yeah, I mean, that's why I think, I mean, that's one of the problems that I don't know how to tackle at this moment, because here it seems that it's breaking at several places at once, but somehow it's still a single composition. So you would like it to be a codimension 1 boundary. But I mean, the only reasonable thing seems to be you just formally construct some simplicial space where codimension 1 faces look like breaking possibly at several places, but all of them have a simultaneous gluing parameter. And you can add that simplicial, like that using simplicial space and symplectic cohomology, but how to get a nice model is not clear to me. Yeah, I'm sure I was very helpful.
Thank you.
Okay, so let's think Yash one more time.
Thank you.